Okay, welcome back everyone. Nick Russo again, and we're going to talk in detail about state this time. State is kind of on the surface, I think most of us can understand. We're measuring the quantity of information retained in the network. And we might be looking at this kind of holistically, how much state is spread across all of our devices and taking an aggregate sum. We might just be focused on one device. We might be focused on just one part of one device's network operating system. It really depends on the scope. But in general, we're trying to measure the quantity of information. The other thing about state that's not as well known is the speed at which that state changes, or the speed of information change. Because state that is constantly churning plays against, or I should say increases total state. So for example, if you have a whole lot of MPLS traffic engineering tunnels that are very stable, they don't change very often, maybe it's a very stable network, that's different than a network with many TE tunnels that constantly flap, or that constantly have to be recomputed, or that constantly need to be resignaled because the constraints have changed. So those two networks have a very different profile in what their state makeup looks like. Here's an example, and I'm going to spend some time on this one because I think this helps illustrate when we talk about state with something very obvious. I'm going to use a lot of QoS examples, so this is going to be kind of thematic through the whole course, is when we talk about different QoS models kind of at a high level. Let's think about integrated services, or IntServ. We talk about IntServ, it's kind of a reactive-based QoS control plane where clients or stations, in this case I'm just using phones, will request resources from the network. So for example, station 1 wants to talk to station 3, and I'm just using telephony terms here just to keep it simple. Station 1 says, I need 80 kilobits per second to do my phone call from station 1 to station 3. That first hop router is going to process the message, and that information needs to be retained across the whole network. This is a very small network, of course, but each router needs to honor and respect that bandwidth reservation between those two nodes. Otherwise, the application isn't going to perform the way it needs to. So this state is one particular flow on one particular device as part of one particular application that the whole network needs to know about. Clearly, this is a very, very high state solution because all the devices need to know about all the flows. Now, the network can reject requests. It does have some authority, but that doesn't necessarily help what the application does. So let's just assume for a second that all these devices need to retain all this different information. Okay, that's obviously a lot of state. So I'm trying to show an example here of something that has a lot of state. And again, I just want to clarify, don't think too much about RSVP yet. I mean, yes, that is the protocol that we typically use for IntServ. We're going to talk a little bit about how the messages work later, kind of in a different context. But we're assuming oversubscription is not configured here, and I don't want people to take this too literally. I just want to show kind of a high-level example. Let's look at Diffserv now. Again, very similar diagram, but just a little bit different. I like to think of Diffserv as an in-band alternative, whereas IntServ was an out-of-band kind of separate control plane. We have another protocol that manages our reservations for us, and once those reservations are cleared, we're allowed to send traffic through the network. With Diffserv, differentiated services, we're going to embed in-band the quality of service treatment in the packet itself. So every single packet needs to be marked somewhere, and through the network, the devices will statelessly determine what that treatment needs to be. So I just need to go on every device, and for every queue that I have, or for every marking I care about, create some kind of QoS policy that gives the traffic the performance or the treatment that they need. This is an extremely low state solution because the devices don't need to maintain any state for any of the flows, at least for the transit flows going across them. Part of the reason why Diffserv, I think, took off in general is because the stateless nature of it made it really well suited to large networks with diverse applications, and we can kind of group applications together based on their per hop behavior. That's kind of the whole idea of DSCP, or Diffserv in general. So this is probably one of the simplest possible examples that I can show about network state, whereas with IntServ, we saw a very high state solution, and with Diffserv, we see a very low state solution. One of the things that I like a lot about this model is it gives us a lot of opportunity to ask questions about, well, if I have a network and it's in some certain condition and I want to maybe reduce other negatives. So let me try to explain this a little bit better. If you deliberately increase state, it should lead to a reduction in de-optimization, or it should increase your optimization. So again, if you increase state, you can decrease your de-optimization, or you could reduce your surface interactions, or possibly both. And what we do in this course is we're going to examine a lot of different examples on how we can maybe increase one, so basically trade off or make worse one attribute to make another one better. So you may inherit a network like the one on the screen where maybe it's already a pretty low state network and you don't have state concerns, but you actually do have optimization problems that you need to solve. So your boss might say, hey, your boss is not going to come to you and say, I need you to increase state to decrease the optimization. This is what you're going to think about in your mind and determine whether that trade-off is really worth the risk. Or I shouldn't say the risk, it's whether worth making that trade-off. So let's examine an example here. Here's an example of increasing state that also decreases de-optimization, or put another way, increases optimization. This is a very simplistic example. And I'm just going to kind of summarize this as if it were a short story. A network operator leaks some IS to IS level 2 VoIP routes. So you can see I got VoIP networks on the left, and maybe I leak those into my level 1 over some low latency links that I have. So by default with IS to IS, normally those border routers, the L1, L2 routers would just originate default routes through the attach bit into all the level 1 devices, and we'd end up with just multiple default routes. So in this situation, I'm going to leak routes from level 2 to level 1 explicitly to use longest match routing to get traffic to move from right to left over the low latency links. Clients in the layer 1 domain follow these longer matches, as I said, to get back to the data center where their VoIP network is, or their PBX, or whatever applications they've got running. Now we've increased the amount of state in the network because the information hiding that the level 2 router at the top used to do is no longer there. So we've deliberately increased state to decrease de-optimization. So in this particular environment, we had a business constraint or a customer pain point or some reason to do this, but we analyzed why it made sense, and we said we acknowledge that we had to make this complexity trade-off. Now the question that some people might say is, well, is this more or less complex than not doing the leak? And this is where I think it gets a little bit tricky, because it's hard to just make generalizations about being more or less complex. It's just different. That triangle, that dot in the triangle moves a little bit. It moves away from the edge that says state and towards the edge that says de-optimization. In this case, I only leaked one prefix, hardly the end of the world. So that dot may have only shifted just a tiny amount, but you just want to be cognizant about how it moved and why, and be able to make those analyses. Another example is we could also increase state with the specific objective of decreasing surface interactions. This one's a little bit more difficult to explain, but I look at this as like a hybrid SDN solution. So consider this. An organization has deployed a network-side SDN solution that uses a fully centralized control plane. Okay, so all these individual devices in the network are receiving effectively commands from their SDN controller on how to forward traffic. The network is entirely dependent on those SDN controllers and then the northbound business applications above those controllers for all the traffic forwarding. That sounds really cool. Sounds modern, right? Well, maybe that dependency is causing a risk to our business, either due to outages or some kinds of problems. So maybe we want to increase state by allowing a more hybrid design, which allows the routers to maintain their own ribs and fibs on their own, i.e. their own control planes, and they can do their own, I shouldn't say ribs and fibs, I should say maybe they run their own routing protocol still, and they only get augmented from the controller. So for example, the controller says, hey, use these policies for these clients. I'm still going to send you all the flows in the network so you can do real control, kind of centralized SDN. But if you can't talk to me, kind of like that top router lost its control plane connection back to the controller, it can still be used, or it can still be used for forwarding because it has local control plane. Of course, this is going to increase state, but I've decreased the surface interactions. And you might say, well, how did you decrease surface? I broke dependencies. So this solution used to be very tightly integrated where the forwarding devices completely relied on the controllers. Now they no longer do. I've increased the autonomy which means I've decoupled the devices. Now, some people might say, well, SDN decoupled the control plane from the forwarding. Yes, it did, but it creates a new surface interaction in the form of a dependency. And we'll talk more about that later. But this is just one example of if you intentionally are increasing state to reduce some other negative, this would be just an example of how you would do that. A little more complicated to understand is the speed of state. So I think it's self-explanatory when you look at it in isolation, but it requires, I'll call it a deep examination within the context of this model. So let's look at just, this is an example using BGP and some timers. And again, I'm oversimplifying this in a way because this isn't a BGP optimization class. It's just discussing about how speed of state works. So through a variety of event-based and pole-based, and when I say event-based, I mean an event happens and there's a trigger versus pole-based like timer. Networks can react typically to a variety of conditions that require the control plane to reconverge, like a link or a node failure. So in this case, on the left side, we see a link failure from RAS, which is the iBGP, and then I have an external BGP peer to some other device. As we tune these if we tune these to happen faster, for example, BGP next hop tracking or any other timer-based thing, and even though next hop tracking is kind of event-based, where I'm getting with this is when a next hop is withdrawn, how long do we want to wait before purging those routes? If we decrease that number, so if it responds faster, that counts as an increase in state. So think about it. If a BGP peer goes down and I say, you know what, wait 5 seconds, because what if that peer comes right back up? Well, if the peer comes right back up, then there's really no point in the other 1,000 routers in the AS recomputing BGP and going through all the BGP churn if I'm just going to come right back up on that link. If you have requirements for extremely fast convergence, 5 seconds might be unacceptable, in which case you are increasing the speed of state, which means that you're generally increasing state. So you just need to keep that in mind that, again, this might be another example of reducing de-optimization, or should I say increasing optimization by reducing these timers. So again, you'd be increasing the speed of state to get better convergence. That's totally valid decision. Just make sure you understand it within the context of the model. Now, keep in mind also that speed of state doesn't just have to be about routing. It could be even within software processes. And I don't want to get too much into it because I don't have great examples, but you can also think about maybe a complex software application that has multiple threads that have to share information back and forth. It might make sense to wait certain things or to batch some things together, for example, writing to a file and things like that. So consider speed of state also as another dimension when you're assessing the state of the network. Next time, we're going to talk about de-optimization, so stay tuned and we'll jump right in. Thank you.